Good morning, everybody. Let's get started. There's still a lot we have to do, so let's see how far we can take it today. As always, let's remind ourselves as to what we did last time, and then we will continue where we left off. So, we are currently on a quest. And our question is, given a set of higher dimensional points, in our case so far, these sets of higher dimensional points were indeed sets of two-dimensional points, which is higher than one-dimensional, and we thought of them so far as the pixels in a binary image, just to have some intuition as to what we're doing here. Given this situation, that we are dealing with a set of higher dimensional points, we are on a quest, namely towards answering the question, is there a coordinate system implicit to the set of points we are given? And by that I mean, well, whenever we are given a collection of points, you can think of them as, vectors. And on a digital computer we have to represent them in terms of, say, higher dimensional arrays, or a matrix of column vectors, which is basically to say a collection of numbers. And these numbers have to have been measured in with some coordinate system in mind. So for instance, every point in this gray shape here can be expressed in terms of its, say, x and y coordinate, right? And our question is, in addition sort of to the canonical x and y coordinates, in which, for whatever reason, the data we are given is being expressed right now, is there another coordinate system that would allow us to express the data in a way that is caused by the data itself? And one of the fundamental ideas in this regard is to look for what is called the major principal axis or principal axes of this collection of points. And in this sketch I have already shown it. It is the orange line here. This is a line, an axis, that is defined by the shape, by the collection of points, because it minimizes a certain criterion. Say, once we have found this axis, how could we find another coordinate axis? What would be a good idea? So we are dealing with two-dimensional data. We have found one axis. How to determine another one?
Perpendicular.
Exactly. Once we have found this one, the second one would just be perpendicular to that one, right? And there we go. So, this again summarizes what I just said. We are given a set of two-dimensional points, data vectors in our case, and we can think of them as the pixels in a binary image. This is so far just, to have a mental picture as to what is going on. And last time we indeed began to look into the problem of how to compute the optimal choice of theta and rho in a situation like that in 2 dimensions. And we found two incredible things based on geometric considerations. First of all, we found that this axis we are after, the major principal axis, passes through the mean or centroid of the data. And I said this is better than actually trying to compute this parameter rho, this sort of offset of the line from the origin. If we know that this line will pass through the mean, which is probably here, that is likely better. So we don't care about this parameter rho anymore. And the second thing was that we found this major axis to be tilted by an angle theta, which is given by 1 over 2 times the arctan of 2 mu 1 1 over mu 2 naught minus mu naught 2, where these mu's were the central moments, second order central moments of the collection of points. As you already said, you know, like once we have this axis, the first one in the case of 2D data, the second one is trivial, it's just perpendicular to this first axis. Now, how can we use the information we uncovered last time to say transit from the original coordinates to this intrinsic coordinate system? Say we are given a collection of points, which again, just for visualization, I'm showing you here as a binary image. We can then, you know, compute the mean of this collection of points or of this binary shape and subtract it from every data point. That would move the shape or collection of points to the origin, as in here. Once we have sort of, either we move the shape to the origin or we sort of come up with a new coordinate, you know, two different points of view on the same effect. Once we have transited to this coordinate system, we can then rotate every point about the angle theta, or we may rotate the coordinate system, again, 2 points of view for the same effect. And we would then end up with a representation of the data we are given as shown on the right-hand side. So indeed, we can think of this as some normalization process. Whereas it is not entirely clear why the collection of points should appear like this in this coordinate system. Here, at least, we now represent them in a coordinate system that is, in a sense, canonical with respect to the data. And we then moved on because what we are really after here is a deep understanding of what it is that we are doing when we are doing things like that. And we already began studying a different approach towards obtaining these parameters of this coordinate system. We already know it has to pass through the mean, but how can we compute that angle theta? We are about to study another approach. And in preparation for that, we had a look at the effect of basis transformations on operators. And that is to say, if we assume that we are given two arbitrary real-valued vectors in n dimensions, which are expressed in some basis, and there is an operator which, if it acts on x, produces z, we can then think about a basis transformation that transforms the basis b into a basis b prime, and say this basis transformation was accomplished by an operator m. That is to say, given vector z expressed in the basis b, we might multiply the matrix m, this operator, to z and obtain z prime expressed in the basis b prime. Of course, we can do the same for x and would get x prime. I said this operator ideally was invertible. That is, we can go back and forth between the two basis systems, which is to say, if we know that z prime equals m times z, then by inverting this operation, we would obtain z as m inverse applied to z prime. Now, with all of this, we now know that z can be expressed as m inverse times z prime. At the same time, it can be expressed as a times x, so we have the equality that z equals m inverse z prime, which is the same as a x. And for this x, we know that it can be expressed as m inverse times x prime. So by plugging in this result in here, we basically get that z is a times m inverse times x prime. And well, or we can say that m inverse times z prime is a times m inverse times x prime. So if we now then finally multiply this equation with m from the left, we get that z prime is m times a times m inverse times x prime. And if we introduce a new name for this product of three matrices, let's say A prime, we find that if the relation between Z and X in the original basis is given by the operator A, then in the new basis it is given by this operator A prime. And the important form is that this A prime actually is a matrix that results from multiplying the original matrix A to this basis transform, to the inverse, and then multiplying this basis transform to A times M inverse. All right? This is indeed just algebra here. The second approach towards computing this principal axis we began looking into last time is based on the idea of diagonalizing a covariance matrix. Right? And if we are given this covariance matrix, in our case still two-dimensional for the sake of simplicity, can express it as a matrix whose four entries are given by the second order moments of the data set we are dealing with. And only for brevity, throughout our lecture today, I will write these three numbers as A, B, and C. Right. This is because I am too lazy to always write the mu's with their subscripts. At the very end, I will then reverse this sort of substitution here. Okay, so the covariance matrix is a 2x2 matrix. And we are now interested in a basis transformation such that if we transit to a new basis, this matrix C becomes a matrix C prime. Right? This is exactly what we did on the previous slide. This time, instead of A, it is C. And if we have this basis transformation, we get a matrix C prime. Instead of C prime, however, I will henceforth write a capital lambda. This is the Greek letter lambda, and I'll do that because everybody does it. Right? I'm just using this C prime here to make the connection to what I discussed earlier. From now on, this new covariance matrix, this is a transformation of the covariance matrix. From now on, it will be called lambda, and we are actually interested in a transformation such that the matrix lambda we obtain after the transformation is of this form. It is supposed to be a diagonal matrix, which is to say that only along the diagonal are the elements of lambda different from 0. So the off-diagonal elements are 0, and of course in a 2x2 matrix this is rather trivial, but we can also think of diagonal matrices in higher dimensions, so say n by n or whatever. Off-diagonal elements have to be 0, then the matrix is called diagonal. This is what we want to have. And again, doing some algebra, we find that this is sort of what defines our matrix lambda, the fact that we are looking for a transformation T such that T times C times T inverse gives us lambda. Again, we do assume that T is invertible, otherwise we could not even express it like that. Now then, if we multiply both sides of this equation with the inverse of T from the left, we get C times T inverse equals T inverse times lambda. And again, just because of my laziness, I am way too lazy to write T inverse all the time. And so therefore, it shall be called V from now on. All right? And for the time being, all of these matrices are 2x2 matrices defined over the reals. And in particular, we can understand this matrix V as a matrix consisting of two column vectors. Of course, both of these column vectors are two-dimensional vectors. And I will call these two column vectors V1 and V2. And they are two-dimensional vectors. Now then we can express this equation as C times V is C times the matrix whose first column is V1 and whose second column is V2. If we compute this product between these two matrices, we find that it will result in a matrix where the first column is C times V1 and the second column is C times V2. And on the right hand side we have matrix V times lambda, but since lambda is a diagonal matrix, we can express this matrix here as a matrix of two column vectors where the first column vector is just a scaled version of V1, scaled by this value lambda 1, and the second column is a scaled version of V2, scaled by this scalar lambda 2. Now, if we look at that, in order for this equality to hold between this matrix and this matrix, we see that the first column in this matrix has to be equal to the first column in this matrix, and the second column in this matrix has to equal the second column in that matrix. And this is to say that we are dealing basically with two equations here. Both are of the form C times Vi equals lambda I times Vi. And I assumes a value of 1 or 2, depending on what column we're talking about. And this is a very crucial type of equation. It is an vector eigenvalue equation. Whenever we see something like that, and there is an equal sign in between, then we know if these two things are equal, that Vi is called an eigenvector of that matrix C, and lambda I is called an eigenvalue of C. Yep, and that was everything I wanted to recap, and we will now take it from here. And I do not know if all of this is basically old and boring to you. Actually it should, but if it is not, which is my experience, that years and years ago when I talked about all of this, I didn't actually talk about this. And I started with what we are going to do next time, and I found that it led to confusion on the part of the students, and I cannot risk that, so I have to do this sort of from the bottom up, from the very bottom up, because what I really need you to do is to totally, utterly, fully understand and grasp what we are doing here. If by the end of this semester you are comfortable with the stuff we're discussing right now, then you have learned something. Okay, let me repeat this really crucial equation we have here. So we are at the point where we have found that C times Vi is the same as lambda I Vi, this eigenvalue eigenvector equation. And I have called this one equation 1 on the slides. And the very first thing we note is that, well, let's do it like, I'll do it step by step. This is really so crucial that you follow me, so let's do it. We can subtract this vector from the right hand side. All right? So we have C times Vi minus lambda I times Vi is equal to the zero vector. If we look at this, we might be tempted to factor out the Vi, right? Because it appears in both these terms. However, here there is a matrix and here is a scalar. So how would we factor it out? Because, you know, if then we sort of have difference between a matrix and a scalar. But note that we can, you know, think of it like this. This is C times Vi minus, I don't know, let me lambda I times the unit matrix times Vi equals 0. Right? Whenever there is no unit matrix, we can simply insert a unit matrix. Now we have matrices in both terms, and so I can factor it out. This is to say that the matrix C minus lambda I times the unit matrix times vector Vi gives the zero vector. All right? And this is to say, I will call this one 2. And this is to say, while we're at it, we can, you know, introduce some more terminology, that the so-called kernel of this matrix C minus lambda I times 1 cannot be the set only containing the zero vector. And when I am talking about the kernel, I am referring to this concept where the kernel of some matrix, let's call it A, is the set of all vectors V, let's say we're talking about n-dimensional, n by n matrices, so it's a set of all vectors V, such that if we multiply A to V, we get the zero vector. This is the definition of what mathematicians call a kernel. Unfortunately, there are many things called a kernel in math and in computer science. For instance, you may be using Linux or Unix, and you have Linux kernel. This has nothing to do with this kernel, right? And the kernel functions in the kernel track have nothing to do with this kernel. This is extremely unfortunate, but it is like that. Really, I don't fully understand why people would not come up with other names. But this is to say, let me, you know, this is all good to know. That is, if the kernel of a matrix is not just the set containing the zero vector, the, well, trivial vector 0 is not the only solution to the equation A times some vector V equals 0. If the kernel contains more elements than just the trivial solution, because, you know, if we multiply some matrix with the zero vector, we get a zero vector. That's trivial. If there are more solutions to this problem, then the kernel of A contains more than just one element. And this is interesting because in order for A to be invertible, it has to be 1-to-1. Right? So for sort of, we apply A to some vector, we get a result, and if we can sort of invert that operation that is given some result, we sort of apply A inverse, we get the original vector back. If, say, there were several solutions to this problem, then if we were to apply A inverse to the zero vector, we could never get the original vector back. This is to say that if the kernel contains more than just this vector, the matrix A is not invertible.
With the equation 2, we could also say because this matrix vector operation gave us 0, so matrix should be singular or something?
Exactly. Yeah.
So that means that this matrix is not invertible.
This is not invertible, and I was just to write it down. but very good, very good. So, is there something else we do know about matrices that are not invertible? Exactly. If a matrix is not invertible, that is to say, if a matrix is singular, its determinant vanishes. Right? So the determinant is 0. And having discussed this, we can therefore say that equation 2 I have just erased is equivalent to saying that the determinant of this matrix C minus lambda I times unit matrix is 0. Right? And this is exactly because this matrix is not invertible. And we discussed that. Okay, let me create some space. In other words, we are now at the following point. In other words, the determinant of the following matrix, and I'm using this A, B, and C stuff. So A minus lambda I, B, B, and C minus lambda I. Right? This is matrix C minus lambda I times unit matrix, given what we had on the slides. Well, what is the determinant of a 2 by 2 matrix? Basically, this entry times that one minus the product of the off-diagonal elements. So we have A minus lambda I times C minus lambda I minus B squared. And all of this has to be equal to 0. Well, that is what we figured just out. And now I will factor out this product here. And it is so crucial, I need more space. So we are at this point right now. I will now compute A times C minus A times lambda I minus lambda I times C plus lambda I squared and so on and so forth. So I'll just write it down. Do you already know how this thing is called?
Quadratic.
It's a quadratic, yeah, that's true. Yeah. With respect to the matrix I just erased? No. Okay, so then it's good that we are doing it this way. Note, this is really crucial, the polynomial. Polynomial. And now I'm again computing the product here. Lambda I squared minus lambda I A plus C plus AC minus B squared I just computed it out, right? Is called the characteristic polynomial of that matrix C. So note that it is called the characteristic polynomial of C and not the characteristic polynomial of C minus lambda I1. Right? This is the characteristic polynomial of matrix C. Let me see if the red one is more opaque. Yeah, it is. Just for readability, I will now switch to red. No semantics attached to that. Yeah, I should not have erased it so vehemently, but now we are dealing with the quadratic polynomial. We can easily solve for lambda. Right? Let's do it. We find that lambda I equals a plus c over 2 plus minus the square root of, what do we have? A plus c, we need to square that over 4 minus ac plus b squared. And then we can get rid of all these 4's in here, and let me, you know, I'll make it nicer. You verify this at home. So verify at home. In the end, this will be a plus c over 2 plus minus 1 over 2 square root of a minus c squared plus 4b squared. Okay. And now, ever so briefly, I will, let me see how I will stick to that. Yeah, okay. This intermediate point, ever so briefly, replace the A's and C's with central moments again, so that we have a glimpse at where all of this is heading. In our specific case, we have that lambda I is mu 2 naught plus mu naught 2 over 2 plus minus 1 over 2 times the square root of mu 2 naught minus mu naught 2 squared plus 4 mu 1 1. So this is a point where I'm not too lazy to write it all out, but basically I'm just using A, B, and C because I am too lazy. Here we already note that stuff begins to look familiar. I have like this mu 2 naught minus mu naught 2, stuff like that we have seen earlier. Let's see where all of this is taking us. Now then, I'll actually say now then. Now then. I'll write the matrix C again as A, B, B, and C. This is the matrix C we are talking about. And we have V11, V12. Let's say this is the first eigenvector. And I'm writing it in terms of its two components. This is supposed to be the same as lambda 1, v11, v12. It's maybe a bit unhappy that I'm writing v11 or v12, maybe it should be v21. But this is supposed to be, the first index counts the number of the eigenvector and the second one counts the dimension. Probably I should have switched that, but deal with it. It's okay. It's a matter of how we call it. Okay, but if we have a matrix vector equation like that, we can understand it as two equations, right? In order for this to hold, the first row on the left-hand side has to be equal to the first row on the right-hand side, and vice versa for the second. So, therefore, or hence, for the first row, we have, we write it out. So this is A times V11 plus B times V12. So A times V11 plus B times V12. And now I am using what we just found for lambda on the previous whiteboard, and I will assume A plus C over 2 times V11 plus 1 over 2 times this nasty square root times V11. So what I have done here is, on the previous whiteboard we had two solutions for lambda I, right, with the plus and with the minus. And well, basically we are looking for two lambdas. We are looking for lambda 1 and lambda 2. And I just declare lambda 1 to be the solution with the plus. And then I plug in our result for lambda 1 here and compute this product, and we get this. Okay, and note that this square root is of course not empty. It contains stuff, and what it contains was on the previous whiteboard, but laziness takes over again. So for a couple of rows we will just have empty square roots. Of course they are not empty, all right? Yeah, I'll sort of, I would just, basic ideas. What I just erased is the same as if we were to compute A minus A plus C over 2 times V11 plus B times V12, and here we have 1 over 2 times this nasty square root V11. How do we get rid of the square root? We square both sides of the equation. So, okay, I'll do it like this. This squared is the same as, well, yeah, something here squared. You verify that at home. So I have now squared both sides. You can do that at home. In the end, like this continues like this, and in the end we find something like the following. Let me skip a couple of steps. V12 square minus V11 square plus A minus C times V11 V12. And all of this is supposed to be 0. So this is, I'm just using algebra to do something with the line we are coming from, getting rid of the square root, lots of intermediate steps. Check out that if you do the algebra, you end up with this. Okay? Do you want me, I mean, like, I really don't know. For the next recap, should I put the intermediate steps on the slides? It's really maybe not necessary, but maybe you are more comfortable with it. I don't know. Verify these things at home. Okay. Okay, we have now just erased something that involved V11s and V12s. And on the right hand side there was a 0, so the question is, can we say something about these still unknown variables V11 and V12? And we can indeed continue where we are and, you know, continue with lots of algebraic, nightmarish substitutions and so on and so forth. I will take a shortcut. I will sort of abbreviate everything and make use of the following trick. Now, here's a trick. And it's valid, right? Let us suppose this first eigenvector, the one we are currently dealing with, this one here, V11, V12, is a unit vector, which is to say that we want the norm of V11, V12 to be 1. This is what we want, right? And this is okay, because in order for this vector to be an eigenvalue of eigenvector of this eigenvalue equation, we can easily normalize the vector to be a unit vector and have to factor in that normalization constant into the eigenvalue lambda. Or we can do that. It's no problem. It does not, if you know, an arbitrary vector is an eigenvector of a matrix, we can normalize that vector to unity. It will still be an eigenvector. The eigenvalue has to be adopted accordingly. That's okay. Right? So we can, as a shortcut towards our solution, suppose that that was the case. That the vector we are after is a unit vector. If we do suppose that, we can think about what kind of two-dimensional vectors are actually unit vectors. And if we sit down and think, we can make the following Ansatz, as it's actually called. Beautiful German word. Oh, this is an informed guess. Right? Whenever you read Ansatz in mathematics, it's an informed guess. We can say that V11 should be something like cosine of theta, and V12 should be sine of theta, or could be, can be, right? With this Ansatz, we then have I just realized I was missing a B on the previous whiteboard. I erased something there. So I was too quick. You cannot verify what I erased. There was a B missing. It correctly has to read like this. So then B, sine square of theta minus cosine square of theta plus a minus c cosine of theta sine theta supposed to equal 0. Okay. And we are now again dealing with an equation with sine squares and cosine squares and product of cosines and sines. And last time we already reminded ourselves of some of the addition theorems for sine and cosine, and using those we find that we can rewrite what I had as, so thus this is now involving clever rewriting of sine square minus cosine square, these kind of things, minus b cosine 2 theta, we saw that last time, plus a minus c, a minus c times sine 2 theta divided by 2, supposed to be 0. What am I doing now? It's the same as that. So this is sine 2 theta by over 2. A minus c is the same as b cosine 2 theta. And this is to say that sine over 2 theta, sine of 2 theta over cosine of 2 theta is the same as 2b over a minus c. And this is something we have seen last time, right? Because that is to say, if we solve this for theta, that we have 1 over 2 arc tan of 2b over a minus c. And if we now replace the a's and b's with the central moments, which are just a shorthand for, we have theta is 1 over 2 arc tan of 2 mu 1 1 over mu 2 naught minus mu naught 2. Isn't that interesting? We have uncovered the exact same result as we did last time. This time, however, our vantage point, starting point, was totally different. Right? Last time we were interested in minimizing a certain energy or error function, which was motivated by considerations in physics, and we found that sort of the angle of the axis we are interested in is given in terms of the central moments. And of course, we know that the central moments do appear in these covariance matrices. And I said, well, instead of minimizing this error function, let's see what happens if we try to diagonalize the covariance matrix. That is, can we sort of find a transformation T that would turn the matrix C into a matrix lambda, where lambda is diagonal. And you may have sort of lost the train of thought, but we indeed did that. I'll summarize it in a second. However, the crucial result we uncovered is that this idea of diagonalizing the covariance matrix leads to the exact same result as the derivation we looked at last time. I said we were interested in finding a transformation T that would diagonalize the covariance matrix. Now, where is this T? And this T is given by the fact that we have now found the first eigenvector, which is cosine theta sine theta, where the theta is given in terms of the central moments. Right? The second eigenvector is just perpendicular to this one, right? So once we have, in the case of 2D data, once we have this eigenvector, we can easily come up with one that is perpendicular to this one. I don't know, I inserted a minus somewhere. And that is to say, we indeed are now in a position to look at the matrix V, which in our case is a 2 by 2 matrix with two columns, and 2 columns are the eigenvectors. And from there, we remember that just for laziness, I, instead of T inverse, said let's call it V. This is what we have. We can compute the inverse of this matrix, and then we have the transformation T. So indeed, it was gone from our discussion for the last couple of minutes, but you see in the end, by what we did here, by determining this theta, we determined the first eigenvector. In the case of 2D data, this immediately gives us the second eigenvector. Once we have these 2 eigenvectors, we have matrix V. Once we have matrix V, we have the inversion, like the transformation from the one basis system to the other. So indeed, what we have been doing here was to find a transformation. Here it is, a transformation that diagonalizes the covariance matrix. And lo and behold, this leads to the exact same solution as the derivation we considered last time. All right, now let's take it even further. Right? Let's look at yet another way of how to end up with this solution. And in particular, the solutions or the derivations we will study now are not sort of constrained to the case of 2-dimensional data. Yeah, let me see. Okay. The way we have determined the principal axis, and once we have them, we just look at an axis orthogonal to that, we have looked at so far is really convenient for the case of 2D data. So, if you're dealing with binary images, I'd really encourage you to compute the angle theta like that and use just a simple rotation. What we did here, the particular derivation is not as easily transferable to higher dimensional data. Next time we will see that all of this is very interesting in image processing, in particular if we understand an individual image as a very high dimensional vector and a collection of individual images as a collection of rather high dimensional vectors. And then we can ask what happens if we look at covariance matrices of data like that, and is there an intrinsic coordinate system for a collection of images rather than for a collection of pixels, right? So in preparation for that, let's look at yet another way of getting this solution. We are now studying the idea of principal, getting the principal axis by maximizing a mean squared projection, or let's say projection spread. Let me see. Says mean square. Not so happy with that. I'll have probably to mean squared projection. I'm sticking with my notes now. My mumbling was basically I'm not so happy with my notes at this point. And for the recap next time, I might use it slightly different terminology here. Okay. What I mean is we are dealing with the following problem. We are given a zero mean data xi. And this is my way of saying we are given a collection of data where I ranges from 1 up to some n, and each of these xi is some m-dimensional vector. Whenever I neglect this syntactic sugar like this, it is sort of implicit that we're talking about lots of vectors, and in some arbitrarily dimensional vector space, say n-dimensional vector space. We also said it is supposed to be of zero mean, and that means that the data we are given, I don't know, let me draw it like this, has a mean that coincides with the origin of the coordinate system. Right? The mean of the data is likely this point, which is the 0 point in that two-dimensional plane. We can have that for arbitrarily high-dimensional data, but I cannot picture it. So this is just a picture. It now looks again like the 2D case, but this is just a visualization. And we do now want to maximize a certain expression. So if we're given zero mean data, we want to find a vector V1 that maximizes this problem here. Maximum over all possible choices of V, 1 over n, sum over the I, and now we have the inner product of V and xi, we square that, and all of this should be such that we say the vector V is a unit vector. So we are interested in this one. Okay, what is this to say? First of all, let's have a look. So there could be some vector V, right? This is definitely a vector V, and we want this vector to be a unit vector, which is to say the length of that vector is 1. I'm using the pointy brackets again to denote inner products between vectors, right? And this here is the inner product between vector V and vector xi. And we can understand it as the projection of xi along the direction of v. And we square that, we sum that over all the i's and divide by 1 over n. This is the variance of the projection. Right? This is a variance. This is something we have discussed earlier. And apparently we are looking for a vector v such that if we project all the data along this direction of v, the variance of the projected data is as large as possible. Right? What does that mean? If we so project all the data onto this direction, then say this extreme data point will end up here, and this one will, I don't know, end up here. And it has a certain, variance, like the projection has a certain variance. If we were to look at a different vector, say this one, so that one also defines a line, and project all the data onto this, then actually this one would end up here, and this one would end up here. And this is a longer line segment, or has sort of a greater, like the variance of the position, it's greater than this one. I hope that sketch gives that away. All right. So what we are currently looking for is a direction vector v, such that if we project all the given data along this direction, the spread of the projection should be as large as possible. Right? And we can see that it may be, depending on what vector we choose, say this one, here the spread is not as large as it is here. Right? Our question is, can we solve this problem? Can we find the vector v1 that is indeed the maximizer of this problem? Under the constraint, so that would be easy if sort of these vectors are infinitely large. So in order for this to be sort of, practical, feasibly solvable, we constrain our solution to be a unit vector. This is, we are looking at a maximization problem that is constrained. We have a constraint. We want to maximize over all v, 1 over n, say this variance here, such that the vector is a unit vector. And of course there are arbitrarily many, like infinitely many unit vectors, and we, out of these infinitely many unit vectors, we are searching for the one that maximizes the projection variance. So, I already said it, I'll write it down. For those of you who have never seen these kind of problems, are you familiar with constraint optimization? Okay, this is good. This is really good. For those of you who are not, this is a so-called constraint optimization problem. Constraint is that the solution we are after has to be a unit vector. And it's a very special form of a constraint optimization problem, because the constraint takes the form of an equality constraint. Equality constraint. Right? Because there is an equal sign here. We could also be asking for the vector that maximizes it such that it is, say, the norm is greater than 1. Then that would be a so-called inequality constraint. But here, our constraint is given in terms of an equality constraint. Okay. Now, I will rewrite this inner product, this squared inner product. And we will then see that it takes us back to an old friend of ours. So, rewriting. Yeah, so our problem is called star. I should have put a star here, like so. Please add it to your notes. Like the problem I just erased, maximum such that all of this is called star. I don't know why I forgot it. Now I'm suffering from my forgetfulness here. Rewriting star. Recall or note that when we discussed the deeper foundations of the Fourier transform in the last semester, I was talking about this crazy notion of brass and cats, different way of writing down vectors. Particularly, we can understand this square of an inner product between two vectors, obviously, as the let me write it like this. Product of the inner product with itself, right? Something we discussed last time. So instead of a comma, I should probably have like the vertical line here anyway. So if we square the inner product between v and xi, we have inner product between v and xi times inner product between xi and v. It doesn't matter, like the order really doesn't matter, right? And in our discussion in the last semester, we found that this here is a matrix. It's the outer product of vector xi with itself, right? So another way of writing this, and this is the transpose of vector v, and this is the usual vector v, we familiarized ourselves with that notation in the last semester. But this is to say that the squared inner product between v and xi can also be written as v transposed times xi times xi transposed times v. Okay? I will not continue with that notation, but given what we discussed earlier, you can see that. Okay, but what we are actually dealing with is the following. So we are actually dealing with, I don't know, 1 over n sum over I v xi squared. Given what we just discussed, we can write this as 1 over n sum over I v transposed. We transposed times xi transposed times v, which we can write as v transpose times 1 over n sum over I xi transposed times v. Do you agree? The vector v does not depend on the index of summation, so we can pull it out of the summation, right? What is this? Exactly. There it is again. It's not such a surprise, because what we're actually after is maximization of some variance. But this is what we called matrix C so far. Okay. And one more thing, when I wrote inner product V and V, that is of course the same as the norm of V squared. Right? Because that is usually the norm is defined as the square root of the inner product of something with itself. So if we have just the inner product of something with it, it's the norm square. Okay, now with these two considerations, our problem now becomes the following. Or this is it's just rewriting our problem. So thus our problem is to maximize over all vectors v, and it's actually this expression v transpose times c times v, such that the squared norm of v is 1. So it's still an equality constraint, I'm just writing it in a different way. Okay, and this is the same. This is the same as if I were to say that such that v transpose times v minus 1 is supposed to be 0. Can you see that? I can also write the constraint like that. No problem. We have now reached a crucial point, and we can actually finish this today, I guess, so we're good. Let's see. Problems like this, if you have never seen those before, so we are dealing with an optimization problem. Right? I said in this semester it's all about optimization. We want to find a solution to this problem. We're dealing with the maximization problem here. Not a minimization problem, this time it's a maximization problem. And it is a constraint problem. And it's an equality constraint, and we can also write the constraint like this. Those of you who have never seen these kind of problems, they are extremely fundamental for our civilization. Right? Without being able to solve these kind of things, airplanes wouldn't fly, engines in cars wouldn't be efficient, and so on and so forth. So these kind of problems, they occur everywhere, not in this particularly sort of simple form or simple context we are dealing with right now, but the ability of humankind to deal with these things is at the heart of our modern civilization. So they are extremely important. These kind of things are extremely important, and it is therefore no surprise to see that the toolbox that has been developed over centuries to deal with these kind of things is fairly sophisticated and advanced. This is actually, out of all the sort of constraint optimization problems we can possibly think of, one of the easiest, and actually a rather old one, so solutions to that, or solution strategies to this are very well established. And I will now discuss one particular way of how we can solve this. Right? But again, this is just one constraint, and the constraint is an equality constraint. It doesn't get any easier than that. Problems with constraints like this, with constraints like this, can be solved can be solved by introducing a Lagrange multiplier. And I will call it lambda 1. Just, some name. Of course, we have seen lambda 1s before. But Lagrange, lambda, so there it comes from, right? And so we introduce this, and then by considering the so-called Lagrangian, this is the name of the following function. It is a function L that depends on V and lambda 1. Now let's, I'll check the 1 here. V and lambda, and this function is given as V transpose times C times V minus lambda V transpose V minus 1. Now, what I have done here is that in our problem so far, in the definition of our optimization problem so far, we had a maximization problem under a constraint. We are not totally free to solve our maximization problem, but the solution has to be a vector of norm 1. And so far I have written down these two, the maximization problem itself and the constraint, in terms of two sort of equations. And now I have combined sort of the function we want to maximize and the constraint into a single function. This function is called the Lagrangian, and I can do this in a tricky way like this by introducing this multiplier here. Now, the reason why this works is rather simple. It is not totally intuitive, but it is nevertheless beyond what we can discuss in this lecture. Right? At this point, I need a leap of faith from your part. Just believe me that this works. Right? Why these things are called Lagrange multipliers, and like where this Lagrangian comes from, you can actually look it up at Wikipedia. This is not rocket science, but still, if I were to discuss the intricacies of this, it would take us too far afield. Right? So, I will ignore why this works. I just claim we can do this. Maybe I'll have a lecture note about this. Actually, it's not rocket science, but let's just believe it. So we then, given this Lagrangian, can actually say, well, two necessary conditions that our solution must fulfill are the following. Necessary conditions for a maximum or solution maximum are, first one, if we derive this Lagrangian with respect to V at the solution, this partial derivative must evaluate to 0, and if we derive this Lagrangian with respect to lambda at the solution, this partial derivative must be 0. Now, let me continue here. I'll note that, well, this is actually easy to compute, right? if we compute dl with respect to d lambda, all we have to do is sort of to get rid of the lambda. This is v transpose times v minus 1. This has to be 0, which is of course to say that v transpose times v is 1, which is just, you know, if we derive this Lagrangian with respect to the Lagrange multiplier, we obtain our constraint back. And it has to be 0, and this is exactly what we want. To summarize this intermediate discussion about Lagrangians, give me 5 more minutes and we are done, this is to say, so what we have been discussing for the last couple of minutes is to say that this problem, so we want to maximize over all possible choices of v transpose times c times v, such that the norm of v squared is 1. So this and this here, maximize over all v and lambda, Lagrangian of v and lambda are equivalent ways of casting the problem. All right. Now then, we need to solve the problem, right? And it turns out I will not actually solve it, but stop at one step prior to the solution. Right? But it will turn out that that is okay, because where we will end up in a second is something we have seen before. And we have seen that we can take it from it. All right. From the other optimality criterion, we obtain, and the notion of other will become clear when I write dl dv. This is the other one, right? We had already looked into the derivative of L with respect to lambda, and now we look at the derivative of this Lagrangian with respect to V. And if you look at how we defined the Lagrangian, V transpose times C times V minus lambda times V transpose times V minus 1, if we derive that function with respect to V, we get 2 times C times V minus lambda 2 times lambda times V, and all of this is supposed to be 0. All right? It's actually this 0 here. But this is to say, what is this to say? 2 is gone, yeah? Exactly. This is the eigenvector-eigenvalue problem we have studied earlier. Right. 2 is gone, as you said, so we end up with C times V equals lambda times V. And I stop here, right? We have seen that this can be solved. We actually did it for the special case of two-dimensional vectors. I claim it works in arbitrarily high dimensions. We're actually not really looking into why that is or how that is. When you have to do it in the exercises, you will use numeric software anyway. I know Python has in NumPy and SciPy, there are ways of solving these kind of problems. So let me summarize this, which we recognize from our earlier discussion. Okay. What have we learned today in the last lecture? We are interested in obtaining a coordinate system which in a sense is defined by a set of data themselves. Right? And last time we sort of focused on the 2D case, and I said, well, there's this idea from physics, sort of this axis of minimum inertia, which is called the principal axis of the shape, and we went through it, and we saw that we can actually solve this. Then I said, well, there's another way of finding this solution. We saw that the solution crucially depended on the notion of central moments of the data we're given. Then I said, well, you know, central moments, that somehow invokes the idea of a covariance matrix. Let's see if we can sort of, what happens if we try to diagonalize the covariance matrix. So we started that last time, finished it today, found, gives us the same solution. The interesting thing in contrast to this problem sort of from physics was that diagonalizing the covariance matrix led to an eigenvalue eigenvector problem. Right? And then towards the end of today's lecture, we said, I'll be there in a second. We said that let's look for a projection direction such that if we project all our data along this direction, the spread is maximum. And we formulated that as a constraint quadratic optimization problem and found that the solution of that problem requires us to solve this eigenvector eigenvalue problem. I'll stop here, right, because we sort of have seen this problem before and we just, okay, yeah, from now on it's the same as what we did earlier. So we have already seen 3 different interpretations of what it means to compute this intrinsic coordinate system.
So this means that this problem has more than one solution, as many as eigenvectors.
It has, yeah, okay, so it again depends on the form of the covariance matrix, but say if the covariance matrix is of a full rank, then there will be as many eigenvectors as there are dimensions in the space. Your data can live in a 15-dimensional space, but just cover sort of 13 dimensions, then there will only be 13 eigenvectors. If it really covers 15 dimensions, then you'll have 15 eigenvectors. So yeah, so far we have only always looked for the first one, right? But earlier we saw if we have the first one, we can get the second one is perpendicular to the variance. And so how these things are being solved in general is again sort of beyond what we can do. The important thing is that this structure of the problem re-emerged. Right? And next time we will see yet another way of ending up here. And once we have seen this sort of final way of ending up here, I'll tell you why all of this is very interesting for image analysis. Right? But what I really need you to grasp is the importance of these kind of problems and where they come from. So we've seen computation of axis of minimum inertia. We have seen diagonalization of covariance matrices. We have seen maximization of projection spread. Next time there will be something else. all of this is the same problem. All of this involves covariance matrices. I said covariance matrices will sort of keep us busy throughout the semester. That is all I have for today. Are there any questions? Quick, because the colleague is waiting. Great, if not, then see you on Thursday. Thank you.